Poverty Prediction Using AI, a project by Kaushik Bhavani, Om Jadhav, and Malvinder Nunez. More than 702 million people globally are extremely poor, living on less than $1.9 a day. In fact, the United Nations Development Programme has named poverty reduction as its #1 development goal for 2030. But in order to solve poverty, we must first be able to track it economically. Our goal is to use high-resolution satellite images and ground survey data, feed it to a deep learning model, and use this to predict wealth levels in various areas across the globe, helping governments and agencies better focus their efforts. A satellite image has a lot of information in it. Things like settlement clusters, buildings, farmland, and water bodies are all features that are indicative of development levels in a particular area. So how do we use this data? We use survey data from the DHS program that includes the Wealth Index, geographic data, demographics, and health data for our model. We use data from 8 countries, most of them in Africa, 1 from Latin America, and 1 from Southeast Asia. The cluster data is aggregated taking the mean wealth index of all of the households. The data is normalized for each cluster across countries, and we use a total of 4,300 clusters. For the satellite imagery, we use the GPS coordinates from the DHS survey, use Google Static Maps API to obtain the images, and feed it as an input to our model.
Model selection and results. We're first extracting features from the pre-trained VGG16 network and feed these features to a neural network of 2 fully connected layers with dropouts. To train the model, we're using 6 countries, and to evaluate it, we're using 2. We selected the hyperparameters by using leave-one across validation and doing a grid search for the layer weights. As an example, on the screen we can see the training and validation losses for Myanmar. We got the weights shown on the screen by inspecting all the losses, then we retrained on all the training data. We then evaluated the 2 models on Ghana and Nigeria separately. The plots on the screen show the predicted values against the true values. We then trained new models after doing data augmentation leading up to almost 30,000 samples. Going off from the previous experiments, we trained the 2 networks with the same weights and epochs. Again in the screen we can see the predicted values against the true values. Somehow we got slightly worse results with this experiment. We compare our results against predictions obtained from previous DHS surveys. As we can see, just using old surveys we can do substantially better. But note that these are not always available for every region. The main challenges we faced in this study were related to data collection, obtaining permissions and compiling them, as well as limited computational resources. Some final thoughts: we needed more data, both predictors and target metrics. We could have tried other methods of splitting the little data that we had, and we could have explored other feature extractors and models.